Lecture 2. Algebraic structures of set. Given a non-empty set omega, the collection C of some or all subset of omega possesses certain algebraic structures. We are going to define the following algebraic structures of C. 1. Semi-algebra. 2. Algebra. 3. Sigma algebra. And 4. Pi system or multiplicative system. Semi-algebra, or we call it elementary class. A class of subset C of a non-empty set omega is called a semi-algebra if the following conditions hold. Condition 1. Empty set is element of C. Condition 2. If E1 and E2 are element of C, then E1 intersection E2 is also element of C. That is, we say that C is closed under finite intersection of set. 3. If E1 and E2 are element of C, then E1 difference E2 can be expressed as a finite union of disjoint set in C. That is, E1 difference E2 is equal to the union of Ck as K goes from 1 to n, where Ck are pairwise disjoint set in C. Example number 1. Let omega be a set of real numbers and C be the class of half-open intervals in omega. That is, let C be the set of all half-open interval AB, that it is open on the left and closed on the right, such that A and B are real numbers. Then C is a semi-algebra, since all the three conditions are satisfied. That is, 1. Empty set is a subset of C. Remember, an empty set is a subset of every set. Empty set is a subset of C, since we can write empty set as an half-open interval where A and B are equal. That it is open here, A, and closed here. 2. Let E1 be this half-open interval from A1 to B1, and E2 be this half-open interval from A2 to B2. Both of them are element of C. Let us use this diagram to illustrate these two sets. This is the real line. The half-open interval E1 is an interval from A1 to B1. It is open here and it is closed here. The solid circle here indicates that the set is closed at this point, or the interval is closed at this point, and this circle colored white represent it is open at this point. So E1 is open at A1 and closed at B1. Let this be E2. E2 is open at A2 and closed at B2. Clearly, the intersection of E1 and E2 is this portion from A2 to B1. You can see that this intersection from here to here is open at A2 and it is closed at B1. Hence, the intersection is element of C. So this implies that E1 intersection E2 is equal to the half-open interval A2B1, which is also element of C. Then 3. Again, let E1 be this half open interval and let E2 be this half open interval. Both of them are in C. Let us assume that E2 is a subset of E1. Here is a diagram illustrating this. This is a set E1 which is open at A1 and closed at B1. This is an interval E2 which is open at A2 and closed at B2. Clearly, as you can see in this diagram, E2 is a subset of E1. Now, what is E1 difference E2? Then E1 difference E2, if you remove E2 from E1, that's if you remove from here to here, we are left with this portion from here to here and from here to here. So therefore, E1 difference E2 is equal to C1, that's this portion, union C2, which is this portion. And you can see that C1 and C2 are disjoint. They don't have anything in common. So where C1 is equal to the half open interval A1 to A2, and C2 is half open interval from B2 to B1. Example number 2. Let omega equal to r squared and C be the collection of all rectangles in omega. That is, C is the set of all Cartesian product AB half open interval AB cross half open interval CD such that A, B, C, and D are all real numbers. Then C is a semi-algebra because the three conditions are satisfied. 1. Empty set is element of C, since you know empty set is a subset of every set. 2. Let E1 equal to the Cartesian product A1 B1 product C1 D1, and let E2 be the Cartesian product of A2 B2 as half open interval cross C2 D2. Let these two sets E1 and E2 be element of C. Then what is the intersection of E1 and E2? What we are saying here is that if E1 is a rectangle and E2 is a rectangle, what is E1 intersection E2? You will see that E1 intersection E2 is also a rectangle. 3. If E1 is a rectangle and E2 is also a rectangle, then E1 difference E2 can be expressed as C1 union C2, where C1 and C2 are disjoint and are rectangles. Let us illustrate the properties using this diagram. Here, this is r squared, this space is r squared, and here the product of the interval, half open interval A1, B1, and C1, D1 will form this rectangle. So let this be E1. And also the product of the half open interval A2, B2, and C2, D2 will form this other rectangle. So let that rectangle be E2. Clearly, E1 intersection E2, that is the intersection of this rectangle and this other rectangle, is the rectangle here. This is the intersection. So you can see that the intersection of two rectangles will always form a rectangle. And also, E1 difference E2. That is, if you remove this second rectangle from the first one, we are left with this portion colored blue, light blue. And clearly, if we extend this, you can see that the shape you have here is a union of two rectangles. So if we partition here and call this rectangle 1, that is C1, and call this one C2, clearly C1 and C2 are disjoint. Algebra. Let omega be a sample space, and let A be a collection of subset of omega. Then A is called an algebra if the following conditions are satisfied. 1. Empty set and omega are element of A. 2. If E is an element of A, then E complement is also an element of A. 3. If E1 and E2 are element of A, then E1 union E2 is also an element of A. That is, an algebra is closed under finite union. Theorem. An algebra is closed under finite intersection. Proof. Let ek be element of A for k equals to 1, 2 to n. Then, by condition 2, ek complement will be element of A. So you recall that if A is an algebra and ek is element of A, then ek complement is also an element of A. By condition 3, the union of ek complement as k goes from 1 to n is element of A. We recall that if E1 and E2 are element of A, then the union is also element of A. And here, since ek complement is element of A, then the union of ek complement as k goes from 1 to n will also be element of A. That's by condition 3. Then by De Morgan's law, the union of the complement is equal to the complement of the intersection. That is, this union is equal to the complement of intersection of ek as k goes from 1 to n. That's what De Morgan's law says. And since this union is element of A, which implies that the complement of this intersection is element of A, since this complement of the intersection of ek as k goes from 1 to n is element of A, it follows that the complement of this complement is also element of A. And you know the complement of this complement will give us the intersection of ek as k goes from 1 to n, which is element of A, which is what we were required to prove. Sigma algebra. A collection A of subset of a set omega is a sigma algebra or a sigma field if it is an algebra and it is also closed under countable union. That is, A is a sigma algebra if 1. Empty set and omega is element of A. 2. E element of A implies that E complement is also element of A. 3. That A is closed under finite union. And then 4. A is closed under countable union. Example number 3. The power set of a set omega is a sigma algebra. 2. A equal to the set consisting of empty set and omega is a trivial sigma algebra. Please, you can verify this. 3. Given the set omega of the element 1, 2, and 3, then A equal to the set consisting of the element empty set omega the set containing 1 and the set containing 2 and 3 is an algebra. You can verify that the 3 conditions for a class of set to be an algebra are satisfied. As you can see in this set, empty set and omega are element of A. For every element here, the complement must be there. The complement of empty set is omega, which is this. The complement of omega is empty set, which is there. The complement of this set is the set containing 2 and 3, which is there. The complement of this is this set containing 1, which is also in A. And also, if you consider the final union of the element of this set, they are also there. Empty set union omega is omega. Omega union this set will give us omega, which is there. Omega union this set is omega, which is also there. This set union this will be the set containing 1, 2, and 3, which is omega. Omega is there. So you can see that this set A is closed under finite union. Hence, A is an algebra. Example 4. Given the set omega equal to the set of element 1, 2, and 3, then the class of set A, defined as the set containing empty set omega and the set 2, 3, is not an algebra. As you can see, when you try to check the 3 conditions, empty set and omega are there in A. That's the requirement number 1. Then any element here, the complement must also be there. For any element here, the complement must be in A. The complement of empty set is omega, is there in A. The complement of omega is empty set, is there in A. The complement of this set is a set containing 1, and that set is not there. Hence, the set A is not an algebra. Theorem 1. If A1 and A2 are algebra, then A1 intersection A2 is also an algebra. Proof. 1. Since A1 and A2 are algebra, empty set and omega are element of A1. Also, empty set and omega are element of A2. And since these two are element of A1 and A2, it follows that empty set and omega are element of A1 intersection A2. E element of A1 intersection A2 implies that E is element of A1 and E is element of A2. And since A1 is an algebra, E complement will also be element of A1. And since A2 is also an algebra, E complement will also be element of A2. So this implies that E complement is element of A1 and E complement is element of A2. If this holds, it follows that E complement is element of A1 intersection A2. Then condition 3. We have to show that A1 intersection A2 is closed under finite union. E1, E2 element of A1 implies that E1 union E2 is element of A1. Since A1 is an algebra, that's by condition 3. Also, E1, E2 element of A2 will imply that E1 union E2 is element of A2. Since E1 union E2 is element of A1 and E1 union E2 is element of A2, it follows that E1 union E2 is element of A1 intersection A2. Hence, A1 intersection A2 is closed under finite union. Multiplicative or pi system. A collection C of subset of a set omega is called a pi system or a multiplicative system if it is closed under finite intersections. For example, let omega be the set of elements 1, 2, and 3. And let us define C as the set containing phi omega, please, this X is omega, and the set containing 2 and 3. This class C is a pi system since it is closed under finite intersection. As you can see, empty set intersection omega is empty set. Omega intersection this set is this set 2, 3. So this set C is a pi system. But the set C is not an algebra.